Welcome to another podcast. In this episode, we're going to be taking a look at the error bounds for trapezoid rule. And so I have that formula already ready to go here. So this is the trapezoid rule error bounds. I also want to remind you of the function we looked at together last time. This is the natural log of x squared, and we calculated its value with t6 to be, let's see here, approximately 8.036, and if you actually integrate it out to the three decimals, it's 8.094. So we're off starting in the second decimal, so we're a little ways off on this. So the question I have here is how many subintervals would it take to make the error less than basically out to the third decimal place. And so understanding the question here, what I'm essentially saying is how many subintervals would I have to use? I only used 6 here to guarantee that I'm pretty close out to the third decimal place, within 0.001. So 10 to the negative third is within 1,000th. How many subintervals, in other words, how large should n be in order to make that work? So this is a little bit different than the midpoint rule problem we did. In that problem, I was just analyzing the error. Here, I already know that I've made some error, and I kind of want to figure out how far should I go to make this better. And so in doing that, it's the same formula, almost exactly as midpoint, except remember midpoint rule had a 24 here. Trapezoid rule has a 12. What that means is, and this is important for you to know, midpoint rule commits half the error of trapezoid rule. Because of that, midpoint rule is more reliable, but they are opposite of each other. In other words, if one of them overestimates, the other will underestimate. And so all the values here otherwise are the same. Remember, k2 is if you take the function and look at its derivative on the interval from a to b, in this case 1 to 5, it's less than or equal to this k2 value. And so the first thing I want to do is figure out what k2 is. I've provided us with a nice graph over here. This is the graph of the second derivative of the function f, which the second derivative of this function happens to be negative 2 over x squared. So if you're looking at the function natural log of x squared, its second derivative is graphed here. And so the farthest away, or the furthest away from 0 that this gets is at the point 1, and at the point 1 we are at a value of negative 2. And so k2 is the absolute value of this at the point 1, which is equal to negative 2 over 1, which is 2. And so that is my k2 value. Everything is less than or equal to that point. Nothing gets further away than 2 on this graph from the interval from 1 to 5. So since my k2 value is 2, I can use that to plug into the formula. So I know that the integral I'm looking at minus Tn, this error, I know I want that to be less than or equal to 10 to the negative third. So that suggests that I need k2 b minus a cubed over 12n squared. I need this to be less than or equal to 10 to the negative 3. And the point is, I'm going to want to solve for n. So let's fill in the values we know. We know k2 is 2, we know b is 5, a is 1, and we don't know n. We're going to look for it. And so we want to solve this inequality. So this is 4 cubed is 64. So we've got, on this side, we've got 32 thirds. Is less than or equal to, if I multiply the n squared over, it's less than or equal to n squared over 1,000. 10 to the negative 3 is 1,000. And so this implies that 32,000 thirds is less than or equal to n squared. And if I take the square root of both sides, the square root of this side is 103.28. And so n needs to be greater than or equal to that number in order to make this occur. Because that's not a whole number, we need n to be 104 subintervals. So if I have 104 subintervals, then I know that my actual answer I minus Tn, which is the 104th in this case, trapezoid approximation. So I know that I minus T104 is less than or equal to 10 to the negative third in terms of error. So any error it commits is only going to be out to the third decimal place. Now, this is not a great example of a function that trapezoid rule works real well for. This function, if you looked at the original function, natural log x squared, it has a lot of concavity, and that's bad for trapezoid, just like it's bad for midpoint. So it's not surprising that this thing's sort of slow to converge. But this is the other type of error estimate problem I can ask you to do. I can ask you to find the error given an n value, or I can ask you to find n, like we did in this problem, given the error bound. And so you need to be able to do both problems equally well and understand sort of how to navigate these error formulas. Thank you for watching.